Okay, so today we're going to talk about waves, okay? So basically, I'm going to try to breeze through this quickly. So basically what we see here is we have this wave. We normally see these in like radio waves, any kind of waves. If you do jump rope or you're swinging a string around, you'll notice that it has some kind of like wavy pattern to it, some kind of squiggly pattern. Okay, and so in this case, we're actually observing the transfer of energy. Okay, so waves are really, it's a transfer of energy we're looking at. Okay, we're looking at a transfer of energy. All right, and so here what we see is we have this wave, right, and we have what we call the crest up here. That's the max, and then the trough is down here. Okay, so we call this the crest and peak, and then the bottom is the trough. Okay, and then it intersects right here and comes back. This would be considered one wavelength. Okay, we consider this one wavelength. So from here to here is one wavelength. Okay, because what happens is, and now most people get confused and they say, okay, one wavelength is from here to here, and that's not true. It crosses through the origin and it comes back up to the top. And the way I like to think about this is our negative coordinates, right? -1, -2, so on and so forth, right? And then these are our positive coordinates, so on and so forth, okay? I like to look at it as it has to go positive and negative, okay, for it to be a full cycle or full wavelength. Okay, so this is one wavelength because it goes positive and then it goes negative and it comes back to the original. And then if I really wanted to, I could continue this, and then that would be a half a period, okay, or a half a wavelength rather, so not a period. So right, so this is 1.5 wavelengths we have right here, okay, and wavelength is represented by the Greek letter lambda, okay. It's our Greek letter lambda, and it kind of looks like the squiggle with the line, okay? So, interestingly enough, what we're going to see here is that we have the transfer of energy. We're going to go through some quick problems. So, basically, the distance traveled by a wave during one period is the wavelength, okay? So, this is one period, and basically, a distance within that period is the wavelength, right? So, for instance, I could have a period like this, and I could have multiple, right? Multiple, peaks, crests, and troughs. And this is where it could get confusing sometimes. So let's just draw this, right, dotted line to show the origin, right? Here's one wavelength. There's one wavelength, okay? Because it comes back to the original. So it's actually 2.5 wavelengths. That's what lambda equals, because this is one period. I'm adjusting this to be one period, so it's a ratio essentially, okay? So it could be 5/2 as well. It could be written as 5/2, okay? So as this marker dies, let's get into some more interesting stuff. So if we stretch this out, okay, and we say the midpoint of the wire oscillates, the travel distance, right, because if I stretch this out, the travel distance within the amplitude of A and the midpoint in one period would be 4A, right? Because in one period I have, and the way I like to think of this is I have A going down and A going up, okay? So it's 4A for the amplitude, okay? So basically in between these two, if I measured this out, there's another way I can measure out a wavelength. It doesn't just have to be this way. I could also measure by shifting a phase 60 degrees, right? So I can measure also between crest to crest. Of course I can, because if I took a ruler to this and I actually measured this out, this distance, and of course it's not the best drawing, but this distance to that distance should be approximately the same. And look at that. They are. My finger still lines up in the same spot, right? So it's just shifted over. Okay, and then I could also measure from trough, and if I continued this down, I could also measure from this trough to that trough, right? So I can measure either or here. Whatever I feel like measuring, I can measure. I could also, basically any two consecutive points. So I measure anything that's mirrored. Measure from there to there would work. Anywhere along, as long as it's two consecutive points. Okay, and it's very interesting as we go through with this. Okay, so let's move on. Alright, so I'm going to list some basic wave equations that we'll be using here. The main one we're going to see a lot in this session is frequency equals velocity over lambda wavelength, okay? So we'll see that the velocity over lambda is equal to our frequency, and then we know that period is equal to 1 over our frequency, and right, it's the inverse of our frequency, okay? So if we had to solve for period, we also could use lambda is equal to 2 times the length, right? The length of a string. Okay. Another one we could also use is, and we'll come across this one a little bit, we're going to say that frequency is equal to the root of T divided by M over L. Okay. And this one we'll see a little bit. Okay. And this whole thing is under the square root, by the way. Sorry. So we're going to solve everything inside first and then take the root in the end. Okay. So moving on, we're going to do a quick problem here. Using these equations, okay? So if I'm given a problem like a sine wave travels at a speed v on a string length, right? Length L and mass m, right? So I have mass m, length L, right? And I'm given speed v, right? And if I double a tension force, I do 2 times the tension force, I want to know velocity, the new velocity, okay? So velocity initial is given, and I want to find velocity final, okay? So basically, I'm going to use this equation. I'm going to say frequency is equal to, I'm going to use this one, T over M divided by L, okay? I'm given a mass of 1, I'm given a length of 1, 1 over 1 is 1, and my T is 2 times T, okay? And so I'm solving for my final velocity. Well, my frequency here is going to be root of 2, right? So frequency becomes root of 2 in this case, because 2 over 1 is 2. So, right, so I get root of 2 for my frequency as I solved everything inside first. And then what I'm going to do is I'm going to say, okay, frequency is equal to velocity over lambda, okay? Velocity over lambda, okay? And so I have root 2 is equal to velocity, which I want to solve for, and lambda in this case, lambda is going to be 2, right? So in this case, I wind up getting, I wind up getting this as my answer. I get velocity, because I'm solving for the new velocity, right? So velocity initial, so I have to do my change in velocity, okay? So velocity final minus velocity initial, right? I'm going to wind up getting that velocity is equal to velocity final over root 2, okay? Velocity initial over root 2. That's my final answer. And so I get that because I rearrange this, okay? So I wind up, because my lambda in this case, my lambda I know in the original problem was 2, okay? And so those two 2's cancel out, okay? So I wind up getting, I have a 2 over here, so these cancel out, state change flip, and so I get velocity final is equal to v naught over 2. Alright, moving on to the next problem. So this problem, I'm given velocity, length, mass, and tension, okay? And I'm asked, and I quadruple the linear density. So I'm asked now to find velocity final. And so if I were given this wave, it would look like this, okay? I quadruple this linear density, meaning that this rope is density becomes times 4, okay? So it becomes 4 density, okay? And I want to find my final velocity given my initial. I have my length, right? This is my length. And I have my mass applied and my tension, okay? So basically, I'm going to use the same equation. I'm going to say frequency is equal to velocity over lambda, okay? But unfortunately, I need to find the frequency first because I don't know the frequency, but I do happen to know a couple other things. Like I know I'm going to have to solve for frequency. I know that lambda, right, is, in this case, I think they said it was 2L. Yeah, well, it's 2L because of the equation in this case. So, because you could also, right, because you're basically also, you're going to put this over 2L. So you're going to put frequency is equal to root of T over M divided by L over 2L. You're going to factor in that 2L now because lambda is equal to 2L, right? And so I'm, so I'm dividing by lambda to get my frequency, okay, ahead in advance, okay? So I'm doing velocity over my lambda gets me my frequency, okay? So in this case, I'm solving for frequency is equal to root, I know t is 1, right, over 4 divided by L, okay, and then over 2 times L, right, because I know L is 1, all right, and my linear density was quadrupled, so 4 in front of the mass, okay? That's where that 4 in front of the linear density mass comes from, because that's density, mass over volume, or length, right? In this case, it'd be length, not volume, okay, because it's linear density. So what happens here is I wind up getting velocity, or I wind up getting frequency is equal to root of t over 4L over 2L, and I wind up getting root of 1/4, right, over 2L, okay? So I get 1/4 over 2L is equal to my frequency. And now if I plug that into the velocity equation, I get velocity is equal to root of 1 divided by 4, right, over 2L. And now I'm going to multiply by 2L. That cancels out, okay? Once I get rid of 2L, velocity equals 0.25 or 1 over 2V. 1 over 2V as my final answer. Right, so velocity is actually half in this case, okay? So basically what happens here is I plugged in, I solved, putting 2L in, I was able to solve for lambda. I was eventually able to plug in for lambda, and I was eventually able to plug back in for velocity, because I found frequency was this, okay? And then I multiply by 2L as lambda again, and I wind up getting velocity, okay? So I wind up finding this to plug in for frequency, multiplying by the wavelength, and I got velocity, which was 0.25 in this case. Or, yes, 0.25, so 1, or I'm sorry, it would have been half. It would have been half in this case, not 0.25. I would have got velocity equals 0.5, okay? My apologies. So it would have been root of 0.25 is going to be 0.5, okay, which is half. Okay, so you could say velocity, you could say 1 over 2V, and I actually wrote it there, and I wasn't even thinking. I wrote 0.25. Sorry about that. So it's half V, okay? All right, so we're going to move on to one more quick problem, and then we're going to finish this video up, okay? So this one's a little more complex. Okay, so if you're taking an AP test, there's a good chance that you've seen a question like this already, or if not, you'd probably find this in a general AP book, okay? This is a question that could be a little confusing at first, and so we're just going to analyze it really quickly, okay? So basically, I'm given some values here. I have L, okay? I have a mass dangling, and I have this coil thing, okay? Or this string, actually, okay? So I have this string going on here, this linear string, and I'm asked to find wavelength, velocity, frequency, okay? So given this string, I also am given a few things. I'm given linear density, okay? So linear density, they gave me is 0.05 kilograms per meters, okay? And then they also gave me the mass. This mass is equal to 0.5 kilograms, okay? And then they gave me length is equal to 2.5 meters. And everything's in meters and kilograms and whatnot, so we don't have to convert anything, okay? Everything's where it should be right now, okay? So basically, what I'm asked to do here is I'm asked to find wavelength first, okay? So wavelength. Very simply, like I said earlier, we're gonna pretend this other strand isn't here. So I'm gonna look at it like it's this, okay? Just one strand, okay? But instead, you know, it's bound in between all this, right? So really, this could be actually a little confusing. This isn't the best drawing, but what I could see here is that when I drew this out, right, I have a wavelength going from here, okay? So if I start here, I have one going to there, right? That's one wavelength, right? Now I start there again, and I go to here. That's a second wavelength and a half, okay? So my wavelength, I have 2.5, right, wavelengths in that. And if I also mark that out here, I have one going to here, right? One going to there, and then there's my half, okay? So it's the same thing, it's just I tried to draw this out so it would be a little bit easier to understand. So I have a length of 2.5, and I have 2.5, right, wavelengths within that length. So I'm going to put simply 2.5 over 2.5, right? So I get it to one wavelength, right? Because I have 2.5 meters, right, over 2.5 wavelengths, okay? And I want to get it to one wavelength, right? I want to get it to one period rather, because this is multiple, okay? So when I do this, I guess you could say it like this. I'm going to wind up getting, when I divide away meters are going to go away, even though it doesn't really cancel. But I'm going to wind up getting 1 meter, or 1 meter is my wavelength, okay? Okay, so this is my answer, 1 meter, okay? Now the next one, I'm going to solve for velocity now, okay? To solve for velocity, I could use my equation as I used before. I have frequency is equal to velocity over lambda, okay? So in this case, velocity is going to be what I'm solving for. So I could rearrange this to velocity equals frequency times lambda, okay? And I know lambda is 1. Now I just got to solve for frequency. How can I solve for frequency? Well, guess what? I could use this equation again, where I plug in T over M divided by L. Okay? M over L is going to get me, this is my linear density, that is the length of the string, and T is the tension force. Okay? So tension force in this case is mg. Okay? Tension is equal to mg of the mass over here. Okay? This is mg. They told me the mass is 0.5. So 0.5 times 9.8 is going to be equal to my tension, which really is going to be equal to, I'm sorry, what was it? It was, let's see. If I plug it into my calculator really quickly, 0.5 times 9.8 should be like 4.9, right? So I get 4.9, okay? In this case, it'd be newtons, right? So I get 4.9 newtons pulling down. Right, so when I plug all this in, I have 1 times root of 4.9 divided by, now the mass of my string, that's the next thing. So I have a 0.05 density, okay? So the density is 0.05 kilograms per meter, okay? How many meters of string do I have here? I have 2.5 meters of string. Look at that, dimensional analysis, it cancels out. So I wind up getting 0.125 kilograms is the mass of the string. Okay. So 0.125 goes here times the length of the string, which was 2.5 meters. Okay. And when I plug this all into my calculator, right? So I plug in 4.9 divided by 0.125 times 2.5. Okay. I'm going to take the root of this answer. Ooh. 1 second. Sorry. I was just to divide this. Sorry, my apologies. So when I divide this, so I get 4.9 divided by 0.125 divided by 2.5. Root of this answer, I get 9.89. Okay? 9.89 is equal to my velocity. And guess what? Very simply, my frequency is also equal to this, and the reason why my frequency is equal to this is because it's a frequency of 1, right? Or I mean, my wavelength is 1. Exactly. So if I plug in, and really quickly, I'm just going to do this down here at the bottom, frequency is equal to velocity over wavelength. They want me to solve for frequency. My velocity is 9.89 over 1, right, which equals my frequency of 9.89 hertz, right? So it equals that, and it also equals that in hertz, right? So interestingly enough, there was a relationship between these two. Okay, so I hope that helped make more sense of this. And now the one last thing I want to ask, the one last question, is if I were to put more tension on this string, would it increase, would it add loops, or would it get rid of loops? And so these are the loops going here. And conceptually, if I pull a string tighter, the number of loops usually decrease, right? The reason why, though, is because of my equation, right? If I go back to my equation, which I gave early in the beginning, my wave equation, frequency is equal to tension over mass divided by length, okay? So, and then you could also factor in your 2L for wavelength, right? Because wavelength equals 2L if you're solving, okay? So, but if I look just at this part, right, my tension, if I increase my tension, I'm increasing what's under the root bracket. And if I increase what's under the root bracket, and I take the root of it, I get a smaller number, right? Or depending on what it is. So generally, if I increase my tension, if I increase tension over ML, my density, right? If I increase this, frequency is going to, what's going to happen to frequency? Frequency is going to decrease, okay? And if frequency decreases, well, the number of loops also decrease, right? So interestingly enough, the number of loops will decrease if I add tension, if I apply more tension, because the frequency decreases. And remember, this frequency is best defined as, right, it's like all these loops I got going in here. Oops, that's a really bad drawing, right? Versus something like this, okay, in the same distance and the same D, right? Okay. So this is frequency. I have more loops. I have a smaller wavelength because they're inversely proportional, more loops, whereas here I have less loops but a larger wavelength, right? So I have a greater wavelength, smaller frequency, greater frequency, smaller wavelength, right? And that's true. I see the wavelength is smaller here, okay? So in this case, if I pull it tighter, I'm going to lose the number of loops, which decreases the frequency. Okay, I hope that helped make more sense of things. Thank you for watching, and the next video we're going to go more into radio waves and sound waves. Thank you.